Hello guys, welcome to the second part for the exercises for chapter 3. So today we'll be looking at exercise 4.6 to 4.10. So for the question that we can see here, we can see exercise 4.6, question 4.6. And you can take a second to read the question. Pause the video and read the question. So the question we have here, we have a window that has an internal crack of 2A of 0.5 millimeter. So we have a window. Let's just draw a window. So the window has an internal crack, a crack inside the window of 2A. That's the window, and the material of the window is what? PMMA, which is what? Acrylic. That's the material for the window, and the crack size is equals to 2A is equals to 0.5 millimeter. So one thing I want you to note is that the presence of crack in the material lowers the stress that can be bared by that material. So if there are cracks in that material, there will be stress concentrations on those cracks, making the material to fail below its actual failure stress. So in this question, they are trying to know if this material will fail when it has a crack of what? 0.5 millimeter. So that's what they are trying to access. So the material has a crack of 0.5 millimeter, and they want to know if it will fail at a maximum load of what? 20 MPa. So that's what they are trying to access. So in order to access this, we need to figure out what? The fracture toughness of this material. So what we are trying to achieve here is to prevent this crack from propagating. And for this crack to propagate, the stress intensity factor K1 should be greater or equal to K1C, which is what? The fracture toughness of our material, PMMA. So if this value, if K1 is greater or equal to the K1C of our material, that means this crack will propagate and what? The material would fail. So we want to prevent this from happening. So we have to calculate what? K1C in order to find out if our material will fail. So also another thing, the formula for K1 with respect to K1C is given as C maximum yield strength or maximum strength square root of pi A is greater or equal to what? K1C. So this is the relationship between K1 and K1C. So okay, now that we have this relationship governing K1 and K1C, we know that we have to find the length of a crack 2A, or the length of a shortest crack that will be unstable and propagate if you apply what? The maximum force. So this stress here is maximum. So we are trying to find the value of A, or the value of 2A that will make this material fail. We want to find the value of 2A that will make this material fail. So we make what? A or 2A subject to the formula. So we say 2A is equals to 2 divided by pi K1C divided by rho all raised to the power 2. So at this, so 2A is the value of the crack that will propagate when stress is at what? Maximum. So when stress is at maximum, this is the value of the crack that will propagate, and the maximum stress that is given to us here is what? 20 MPa. So the stress given to us what? Is what? 20 MPa. So what we are going to do next is now plug in our values. So K1C of PMMA, that's the fracture toughness, K1C of PMMA. If you go to Appendix A, you see that K1C of PMMA is given as 1.15 MPa meter raised to power 1 over 2. So that's the value of K1C of PMMA. So we put this into this formula. We have 2A is equals to 2 divided by pi. So this is pi, not x. 2 divided by pi raised to power the K1C, which is 1.15 all over 20 all raised to power 2. Therefore, our answer will now be 2A of 2.1 times 10 raised to power minus 3 meters. Therefore, 2A is equals to what? 2.1 millimeter. So we can now conclude that since 2.1 millimeter is greater than 0.5 millimeter, which is the crack in our material, therefore the crack will not propagate at 20 MPa PA. So that's the answer for this one. If you have any question or if you're confused in any of the steps, please let me know in the comments. I'll get to you. So we'll move on to the next question immediately. Okay, moving on to question 4.7. Take a second to read this question. So this question is similar to the one that we did in question 4.7. So here we have a flywheel. When you read the question, you see that we have a flywheel that is spinning at an RPM of 8,000 RPM. So this is the RPM, or the revolutional velocity, goes to so this is the revolutional velocity of the material, and the material has a radius of r of what? 200 millimeters. And they told us to find out if the material which has a crack of 2a, so the material has an initial crack of 2a of 2 millimeter. Similar to question 4.6, they want to know if this crack will propagate when you're spinning this flywheel at what? 800 RPM. So that's what the question wants to know. If this crack will propagate when you're spinning this wheel at 800 RPM. Similar to what we did in the last question. Okay, so if you read through the question, they are telling us to establish if the flywheel is safe to ride at what? 800 RPM. So all we have to do is what? Compare the crack length that will make the material fail at what? 800 RPM. That's all we have to do here. So we need to calculate what? The stress that acts on a flywheel when you're spinning it at an angle, which is what? Rho max. So the stress acting on a flywheel when you're spinning it at an angle is rho max, or rho m. I'm just calling it rho m. Rho m is equals to 3 plus v, which is Poisson ratio, divided by 8 times what? Density of the material times what? Angular velocity, since it's a spinning wheel, times what? The radius of the spinning wheel, all raised to power 2. Also, angular velocity of this material, angular velocity is giving us 2 pi w all over 60, where w here is what? The revolutional what? Velocity that we have here. So which is now equals to 2 pi times what? Times 8,000 divided by 60, which will give us what? 837.76 radian per seconds. So now we have the value for w, which is what? Angular velocity. We will now calculate stress for this material. So the maximum stress of this material spinning at what? 800 RPM is what? 3 plus the Poisson ratio in the question is given to us as what? Here as what? 0.33 0.33 divided by 8 times the density of this material. So the density of our material, and our material is made up of what? Cast iron. So the density of cast iron from appendix A is giving us 7150 kilogram per meter cube. So this is in kilogram per meter cube, right? So the next thing is multiply by the angular velocity that we've already calculated, 8.37.76 raised to the power 2 times the next times what? The radius of the flywheel, and the radius of the flywheel is what? 200 millimeter. So 200 millimeter will convert to what? Meters times 10 raised to power minus 3 or raised to power 2. So rho m is now equals to 83552.513.76 Pascal. Converting this to MPa, we now divide by 10 raised to power 6, which will give you 83.55 megapascal. So now we have the stress that is acting upon the flywheel when you're spinning the flywheel at what? 8,000 watts RPM. So now, same thing that we did the last time. For a crack to propagate, K1 should be greater or equal to what? K1C. Exactly what we did in question what? 4.6. K1 should be greater than K1C for the crack to propagate. And the value for K1 is giving us what? C rho square root of pi A greater or equal to what? So I didn't mention this in the last question, but C is equals to 1 is a constant for the torsional rotation of a flywheel. The constant is equals to 1. So now we are looking for the value of A whereby if you're rotating the flywheel at a stress of 83.55, which is 8,000 RPM, what is the value of the crack that will cause the material to fail? That's what we are looking for. And we're comparing that with the crack that is already in the material. So in order to do this, we now make what? A subject of the formula. So we know that the length of the crack is usually what? 2A. So we just make what? 2A subject of the formula. So 2A will now be equals to 2 divided by pi raised to power, all in bracket, K1C divided by rho, all raised to power 2. And we know that K1C from appendix A, K1C of cast iron is given as what? 38 megapascal. So this is in megapascal and this is in megapascal. So megapascal dot meter raised to power 1/2. So this is megapascal and this is megapascal. So there is no need for changing the units. So 2A will now be equals to 2 divided by pi times 38 divided by 83.55, all raised to power 2. When you write it out, it will now be 2A will now be equals to what? 0.132 meters, which is equals to 132 millimeter. So comparing this to the crack in our material. So if you look at this, it means that when you spin the flywheel at what? 8,000 RPM, for the crack to propagate, the crack length has to be what? 132 millimeter. But since the initial crack length that we have in our material is what? 2 millimeter, therefore spinning this material at what? 8,000 RPM will not cause this crack to propagate. Therefore the flywheel is what? Safe to drive. So as 2 millimeter crack in our material is less than 132 millimeter, which is the crack length that will make the material to fail, therefore the flywheel is what? Safe. So that's the conclusion. So if you have any question based on this, you let me know. If you have any question based on this, let me know in the comments. But this, okay, let's move to question 4.8. So like I said, take a second to look at the question, pause the video and look at the question. So here we are looking at trying to estimate the diffusivity of polyethylene. So in order to manually calculate the diffusivity of polyethylene. So that's the question and what the question is all about. How to practically calculate the diffusivity of polyethylene. So first, they poured hot water in a pipe of polyethylene. So we have a polyethylene pipe that has a wall thickness of T of 3 millimeters, and hot water was poured into the pipe and one end of the pipe was sealed. This was sealed. Okay. And hot water was poured into the pipe, and we are trying to determine the diffusivity of the pipe, whereby at the time of T 18 seconds, we now start feeling that this edge of the pipe start becoming hot at T of 18 seconds. So you have, this is the wall thickness of 3 millimeter, and you have hot water into the pipe, and at T of 18 seconds, here becomes hot as well. So this is the hot water. So at 18 seconds, here becomes hot as well. So we are trying to determine diffusivity in this material. So in order to calculate this, we know that the formula, the relationship governing the distance x of heat transfer, by a certain amount of time is given by x, which is the distance of heat transfer, divided equals to the square root of 2a T, where A is the thermal diffusivity, is related to the thermal diffusivity of the material. That's what A is. A is related to the thermal diffusivity of the material. So this x is the distance, that means the distance separate of travel of the heat. T is the time that it takes. Also, we know that A is given as lambda divided by density of the material times the specific heat capacity of the material, Cp. So what we are told to find in this question is lambda, and we are given all the formulas. We are given all the formulas, and A, density and Cp of the material, we are going to figure it out from going to appendix A. So in order to do this, we'll first of all make lambda subject to the formula, which is lambda is equals to A density times Cp. Then this initially will now make a subject of the formula from here. We'll have what? A is now equals to x raised to power 2 divided by 2t. Now you have what? The formula for A. You have A here. You have the formula for A. You now combine this equation 1 and equation 2. Combine this equation, we now have what? The value for lambda as x raised to power 2 density Cp divided by what? 2 theta. So this we already know as the distance separating the hot water and the external body. So this is the thickness of the pipe. This is the density of the material in question, which is what? Polyethylene. Cp is the specific heat of what? Polyethylene. Then T is what? The time that it takes the hot water, the heat to get outside through the thickness of what? 3 millimeter. So the density of polyethylene is equals to 950 kilogram per meter cube, and the specific heat is giving us 1850 joule per kilogram per Kelvin. Therefore, lambda is equals to, if you calculate lambda for this material, just add everything into the question. We have 3 millimeter, which is the wall thickness. We now convert this to what? Millimeter to meters. Minus 3 all raised to power 2 times what? 950 times 1850 all divided by 2 times what? The time, which is what? 18 seconds. So we now have what? Lambda as what? 0.44 per Kelvin. So going back to the question, it is telling us to compare the value that we obtain to the listed value of the thermal diffusivity of polyethylene, which have already been calculated. So based on this experiment, we need to compare the results that we got to the standard values of what? Diffusivity for polyethylene. So if you go and look at appendix A and table A7, you find out that the diffusivity lambda of polyethylene is equals to what? 0.4 towards 0.44. Therefore, the value that we got is was the range of what? Diffusivity. So our answer is what? Correct. So moving on to the next question. Okay, moving on to the question 4.9. If you look at this question, you can see that they say that the capacitance of a condenser with 2 plates, each of area A, separated by a dielectric of thickness T. So you have a plate. You have a plate like this, and you have another plate. You have separated by a distance. This is the distance, and you have what? Another plate. So plate 1, plate 2, and it's separated by a distance. Separated by a distance, and they told us that the formula for capacitance C is giving us what? ER, which is what? Dielectric constant times E0, which is what? Permittivity of free space, times area divided by T, which is what? The thickness. Which is what? The thickness of the separation of the 2 plates, T. So they told us to maximize for A. Let us find the material that can maximize what? C. In order to maximize C, we know that we either increase this value or increase this value. So this value is a constant based on the free space, but this value, which is what? Permittivity dielectric constant, is a value related to what? Material property. This is a material property, and these other 3 are not material properties. So in order to increase what? The capacitance, we have to what? Increase what? The dielectric constant. So all we have to do is go through the table for appendix A9 and look for materials that what? Maximizes what? C. So this is straightforward. You can do that on your own. It's a very straightforward question. Then for question B, it's telling us to what? Minimize what? C. Given that for a given value of what? A and T, it told us to what? Minimize what? C. In order to minimize C, you also need to find a value with what? A very low what? Dielectric constant ER. Because all these ones are not what? Material property. All you need what? Is what? ER. So the material that has what? The lowest ER is the best material for question B. So go through the table and find the material with the lowest what? ER. So that is it. Okay guys, for question 4.10, take a second, pause the video and look at the question. Okay, so if you look at the question, we are trying to replace what? Cast iron with a cast iron part with a nylon part. So we are trying to replace a part made up of what? Cast iron. We're trying to use another material, which is nylon, to replace the part. But we want to know if replacing this material, this part with what? Nylon instead of cast iron, will it be cheaper or costlier when we replace this part with a nylon part instead of what? Cast iron. So we know that anytime you go to the market or anytime you want to buy what a material, it has to be in terms of what weight. So if you want to buy the cost of mild steel or the cost of cast iron will be the cost per unit what kg, the cost per kg, that's what we are looking at. So cost is usually in terms of cost times mass. So cost C of a material is equals to cost times what? Mass. So the cost per kg times mass will give us the actual cost of what? The material. So in order to do this, we know that they say that the material has the same volume. So it's going to replace cast iron. The shape is not going to change. The shape will still be the same. You're just changing what? The type of material. So the volume remains the same. So we know that mass is giving us is equals to what? Volume times what? Density. That's the formula for mass. So putting this formula into this, because we're trying to change everything to what? A material property. So cost is now equals to cost times what? Volume times what? Density. Since we know that volume cannot change, it is the same shape, the same size. Only thing that will change is what? The type of material. So we can eliminate cost from what? This equation. So the cost for a material is what? Cost per kg times the density. So the cost for cast iron. Cost for cast iron is giving us what? 7150, which is what? The density kg per meter cube multiplied by the cost per unit kg, which is what? $0.63 per kg. So if you multiply this, you now have the cost for cast iron C. The cost for cast iron CI is now equals to $4,500 per meter cube. That is the cost for cast iron. So cost per unit volume, this is the cost for cast iron. Then the cost for nylon is giving us the density, which is 1,130 kilogram per meter cube times the cost per unit weight of nylon is what? $3.45 per kg. So since we have this, we can now multiply them and see that Cn is now equals to $3,900 per kg per meter cube. Sorry, so $3,900 per meter cube. So now we have this. We can now say that replacing this material, replacing the parts with nylon instead of cast iron will reduce the price. Therefore, using nylon is what? Cheaper than using what? Cast iron. Okay, thank you guys for watching. In the next video, we will be looking at chapter 4, which involves what? Exercise 5 of the exercises. So we'll be looking at more of using what? The Ashby plot to answer what?